Okay, let's be back to the lecture. So, for the design of different types of filter banks, I refer you to the Filschnitt and some other filter bank references. And you can also find different types of examples for that. And probably I'll write down, or I'll give you some references in the website. But the idea is, as I mentioned, so we need to have different channels that can respect the conditions or the constraints that we have in order to have the perfect reconstruction. So if you have the perfect reconstruction possibility, it means that whatever process that you make in the block inside, in the middle block, then you're sure that the beginning block and the ending block will not add that much distortion or aliasing to the signal. So you should just take care about the middle block. And the final structure turns out to look like this. So you have the signal in the input, and here, it looks like using even the two-channel filter bank and taking the structure like this, you can even have your goal respected. So in the beginning, what you try to do is to take the lower frequency and the high frequency part, factorized or separated, and then again for the lower frequency you can have finer resolution. So this is the coarser resolution. This is actually the details of the signal, of the high frequency part of the signal. But the lower part, frequency part, is also again possible to divide it into finer resolutions. We go to the second level. Again, we use the fine and the coarse resolution. And this structure can be repeated onto any levels that is desired for you. And in the same way for the synthesis part, after having this delay is actually compensated, you can have everything in the reverse order. So you have G0, G1, which are the counterpart of this H0 and H1 in the final level. And if you want to have perfect reconstruction with orthogonality condition, the design of these filter pairs are exactly in the same way I mentioned in the previous slide. And then these filter pairs should be designed in the same way, and these filter pairs should be designed in the same way to get the final signal that holds the perfect reconstruction assumption. This is the structure you have to remember, and when we come back to the wavelet, you will see that the wavelet is nothing but a kind of filter bank with different intuition and with different view. So all of these subjects that I put together for this lecture, they are all related, but we will come back to a kind of cartoon that it contains all of these structures in the same place, but how they are discriminated in the time and frequency representation space. So I will skip through the polyphase representation. I already mentioned in one of the lectures about the polyphase, but this polyphase structure is actually the one that gives you the possibility to implement the filter banks, any kind of filter banks, much faster. So already mentioned that polyphase is very useful when you want to have the filter banks. So that's the polyphase implementation. That's the polyphase idea, and next slide is the implementation of the polyphase filter bank. So polyphase is nothing but to actually distribute the h of z polynomial into two different polynomials, for example, in the first place, because it can also be to different levels of different levels of polynomials. But here we just assume that combination of two different polynomials with this structure. we see that that's exactly, if you write it down, spread this and expand this polynomials, we'll get exactly the same thing for h of z, which is h0 plus h1, z minus 1, h2, z minus 2, and so on. So taking pairs of even taps and odd taps into different polynomials will give you this structure. But this part, we name it as E0, sub 0, and in this part we name it as E sub 1. And we show h of z as like this. And if you remember the identity or the noble identities, if you remember this h, the previous slide is actually somehow holds here. So we had the identity that the downsampler and the filter is equal to this kind of filter and the downsampler, and the same for the upsample part. So putting all these together means that in the filter bank design, which you have such kind of structure for the input and the same thing for the output, what you can do is you can replace the, so you know that we have the filter and then we have the downsampler. So you can change the place, and this changing of the places between the downsampler and the filter changes the filter taps like this, which are nothing but the polyphase filters. So we do for all the paths the same way, and also here for this synthesis part. If you do this, then here you have the filters which are in much less taps than what you had in already. So you see that here you have E0 or up to En minus 1 z to the power of n. So it means that you have a lot of more taps than here, which you have m over d. So it means that the convolution or the multiplications of each of these paths is actually reduced by a factor of d, by just replacing these downsampler and the filter and taking the polyphase structure. So it has the effect of d times less multiplication for each of the paths. And you have here, for example, you have m number of the paths or d number of the paths. You have d number of the paths. So that's why we can implement the filter bank much faster. But because we are interested in the perfect reconstruction, filter bank we already mentioned about the conditions and the constraint. The polyphase implementation is just a practical issue that if you want to implement something in practice, then you have to consider it. Let's go to the a new vision of the let's say multi-resolution, or a new kind of angle of view for the filter banks. So the motivation comes from this slide, actually, the information contained in this slide. So we have the frequency and we have the time. These are by far two different concepts that give us the information. Normally the signal that you get in the nature is the time domain signal, but you are interested in some frequency information of the signal to know that. The point is that if you take the Fourier transform, then the information is only localized in the frequency. So it means that you will just know that this signal contains these frequencies or not. That's the only information you will get. But what if we need to know at each moment of the signal what happens? I need to know, for example, at this moment the signal contains these frequencies, and in the next moment, for example, or in 2 days later, the frequency contents of the signal is changing. So there are many applications, for example, as an instance, you need to know the change points. Something is changing. We have friends here, they're working on the brain neurology, and one of the applications is to know the change point of the signals that they get from the brain, because it's important. For example, there is someone, he has a kind of depression and doesn't talk to anyone, but the doctor is talking to him and giving some words, and he reacts to some of these words. So the stream of words is uttered by the doctor, and he will listen, but he has no reaction to any of them. Maybe he doesn't want to give any kind of reaction. He wants to be isolated from the environment around. But in some point, one of these words is very important for him. I don't know, maybe there's a kind of story behind that word. For example, you say a lot of words and then it comes to the mother. And he tries to remind some kind of history that he had with his mother. Then there's a change point in the signal. If you just take the Fourier analysis of that signal, the ECG, KG, whatever signal that comes from the brain, you will never get understanding when exactly that happened. So you will never understand that this changing the frequency, or this component, the frequency component, comes from which of these words. That's just an example. In many, many cases, you need actually to know, or even for the speech case, we have automatic speech recognition, the system that tries to transcribe whatever someone is talked. So we're dynamically changing the state of what we say, and it's changing from the different phonemes to another. For example, I say A, and A is a voiced phoneme, and then I start from A, bo. B is another phoneme which is unvoiced. So what happens? The system should understand that we change from a voiced phoneme to unvoiced phoneme, and then again a voiced phoneme, and so on. So this dynamicity of the system is just tractable and is actually traceable if you have a kind of representation which demonstrates both the time and the frequency variations simultaneously. So these are some kind of applications that motivate using different types of representations, and proves that Fourier analysis, even though it's very useful, but it's not enough. So the goal is, are we able to have a kind of both time and frequency representations simultaneously or not? That's the question. Okay. There are some applications that if you just, all of these things that I said is just an application that brings up the idea of having joint time and frequency analysis at the same time. But there are some other issues that maybe the mathematicians are really interested in, or the computer scientists, and that's the sparse representation of signal. We're talking about a signal. The sparse representation means that if you have a kind of signal or a function, to be able to represent that signal with the less amount of coefficients that's possible in the domain that you are representing. If it's Fourier, less amount of Fourier coefficients, or Fourier series, for example. If it's Z transform, the less amount of Z. DCT, the same thing. So any kind of representation, so we know that signal can be represented based on the bases, the atoms or bases, and the coefficient which shows that how much of that atom should be used to construct the signal. Now, the sparse representation for some kind of signals, it turns out that it's not possible using the Fourier analysis. For example, whenever we have a spiky signal like this, So you have signal, then you have some kind of thing. And it normally happens in biological signals. Then representation of such a signal with the Fourier analysis, with the Fourier series, means to have a lot of coefficients. A lot of coefficients, which finally implies that we will not have the compact support, we will not have a sparse representation of this kind of signal in the Fourier domain. So we are looking for something more compact. That's what motivates using Filterbanks, Wavelets, and multi-resolution analysis. We talked about the filter bank, but it turns out that people look at the filter bank as a kind of structure, as a kind of system. And mostly it triggers the idea of subband coding. But from different angle of view, you can say that even filters in the filter bank structure, those filters are also a kind of basis. But that will be more clear when we go to the wavelets. Then in the wavelet, it's completely clear that these are, we're actually dealing with the basis. And then finally, we see that the structure of the wavelet is quite similar to the structure of the filter bank. But in the wavelet, we call them as bases. In filter bank, we call them as filters. And there is another difference I mentioned here. We will not find time to say that, and that's the point of question. If they are the same, why do we have these two different subjects in the same lecture? Let's give the answer at the moment. Filters are in the frequency domain. So when we are dividing the spectrum into different slices and the filters, just remember this is statements I'm telling you. They are just the important things I'm telling you. And maybe it's a point of question for many other students, even though they know what filter bank is and what wavelet is, they don't know why they should use one with respect to the other. That's the answer. The answer is, when you deal with the filter bank, you're talking about different frequency bands. So at the moment, frequency is the element that you are measuring your signal with. When you talk about the wavelet, there is no issue of the frequency. It's scale. So the idea or the essence of the frequency is wiped out. You're talking about the scale of the signal. Even though it has a kind of correspondence with the frequency as a sense, as the entity. But in wavelet, you're not talking about the frequency. You're just talking about the approximation of the signal and details of the signal. When we say detail, it doesn't necessarily have a one-to-one correspondence with the frequency. But when we say filter band, we are exactly talking about a band for a spectrum of the frequency. So one slice of the spectrum of the signal. So whenever dealing with the frequency components is important. So you're dealing with the F frequency, you use filter banks. When F by itself is not important, just the approximation and details are important, then you will go through the wavelets. In many cases, like the denoising in image processing or the speech processing, you don't care about the frequency, you just care about the details of information, which is not important, and just belong to the noise. You can ignore that using the wavelet transform. So in those cases, wavelet makes sense. But in subband processing, I showed here subband coding in the beginning of the lecture. We have many things in subband processing. For example, beamforming, but subband beamforming. We can go through the wavelet, but we will miss the entity of the frequency, which for us, frequency is very important by itself. So sometimes we need to deal with the frequency, and that's the case which brings up the idea of filter bank to actually, in those cases, outperform or to be chosen as the better idea than the wavelets. Even though they have completely similar structure, but that's the. A multi-resolution analysis is nothing but the wavelets in the kind of strategy. So let's move forward. In the time domain, in time series, you have samples of the signal. You have no notion of the frequency. It means that the frequency resolution is blurred. You have no details in the frequency. You can contain everything. But you have resolution over the time. In the Fourier analysis, the TFT, DFT, whatever, you lose the information over the time. So you have no details about the time. You just transfer from one domain completely to another. But you will know everything about every single component, frequency component contained in the signal. Every single frequency component contained in the signal. And what we want is a combination of these two. Assuming that these are the signals. This is an example of the speech signal. That's an example, for example, a communication signal. You can have many other things. In the first part, for example, that's the stream of the signal, ST, over the time. So at time t1, well, you'll not be able to take a time instant, exactly t1. So you'll look at the signal in the window. So, for example, between t1 and t2, if you look at the signal at this moment, and only at this moment, what you will get as information is a periodic signal, a sinusoid, with the frequency of whatever between these two peaks. That's the only information you get. If you move that to the frequency domain, you will just get one impulse. Nothing more, just one impulse. It seems that this signal just contains one frequency, and that's the frequency. Now you move forward, and you go between T2 and T3. You see that you have two frequencies, one high frequency and one low frequency. You get two taps. So 1 second tap is actually one impulse. New impulses appear. If you go between T2 and T3. Now go between T3 and T4. The same thing happens. Between T4 and Ti, then you will lose the high frequency components and you'll just have very, very smooth and low frequencies. You see that the variation in the signal is very smooth. And then suddenly here, between, for example, Ti and Ta, you see that different other frequencies start happening. For the speech case, this is a sample of a speech case. So you have the voice regimes, which are normally in the dynamic range. In the energy, they are higher energy. They have higher energy than the unvoiced part. If you just take one part and magnify this, this time instant, you will get a kind of structure like this. Looks like to be a kind of periodic. So it contains different frequencies, but it looks periodic. And if you take this part, which belongs to the unvoiced, you see something quite similar to the noise. In most cases, there are unvoiced phonemes which are called pseudo-noise, because it's like a noise. And if you take the spectrum of that part of the speech signal, it actually fully fills out the entire spectrum from the lower frequencies to higher frequencies, and it's like noise. But for the voiced case, it's not like that. There are just certain frequencies activated, and they are normally harmonics. So these are some examples that we localized the signal, the frequency pattern within the time domain. The idea of time frequency representation actually is not new. Whoever is working with the music sheet is nothing but a time frequency analyzer. But they have already learned how to read it. Why? Because they're just working with the instruments. And for the instruments, it's not like the human body, which has a continuous spectrum of the frequencies. But for the instruments, they already know that they are discontinuous, so it's a discrete frequency levels for each of these. For example, if you use the piano, they already know by heart that, for example, that's the frequency that will come out of this key. So when they play something, they already know, but it's, unconsciously they have in their mind. They know exactly, but by the practice. So they can read from this time frequency representation, the analysis. So what is that? It's nothing but the time frequency analysis. You have the windows, which are fixed in time, and they call it, what they call it? Every fixed time period, or the time window, which shows the rhyme of the music which is going to be played. And then, within that period, which is fixed, they are playing notes, which means different frequencies. So they have different frequencies. If it's played faster, it means that there are higher frequencies. If there are different levels, or for example, you impose some silences here, it means that you're lowering the frequency. So that's what musicians already know by heart. Now we want to formalize what they know already in the mathematic form. So the time frequency, as it's written in that music sheet, is like to have the constant windows, the constant window for over the time, and the frequency resolution which is corresponding to that. And we will see later that wavelet is a different representation of this, which says that for the lower frequencies, if I want to have a signal and to get the information for the lower frequencies, for example, there is a kind of lower frequency, the lowest frequency of this signal, if it's the entire signal, that comes from this frequency, from the beginning to the end. So if you take this window to be from the beginning to the end, there is a frequency component that appears that will never appear if you just take a look at every single window. Okay? And that's the frequency of the signal over the envelope, the entire envelope. That's why in wavelet it says that if you want to get the information, the highest resolution over the lowest frequency, you need to have a very large window in the time. You need to have a large window in the time. So you can even have one level further to have the entire T. That takes the lowest possible frequency component. Then you want to go to one level further. So the mid frequencies, you can chop down the window in the time to get the lower frequencies, but not the lowest, the mid frequencies actually. And then you can hierarchically go further and further to get more details. But we know that based on the principle that I'm going to talk about, the Heisenberg uncertainty, when we go deeper and deeper, we have the highest resolution in time. On the other hand, it represents lowest resolution in the frequency. And that comes from the uncertainty principle of Heisenberg. In Heisenberg uncertainty principle, it says that you cannot have the frequency resolution and the time resolution to be fine at the same time. So you have to sacrifice one in the price of the other. If you need time resolution, you have to sacrifice the frequency resolution, and vice versa. So, assuming that the signal is an energy signal, the signal, which is energy, means in the time domain so assuming that the signal is the energy signal, it means that E of x is limited. And based on the Parseval theorem, says that the signal over the time is the same as signal over the frequencies. The energy of the signal over the time is the same as energy of the signal over the frequencies. You will never lose the energy or the information of the signal by just transforming from one domain to another. Okay? Energy is fixed. You're just changing your eyeglasses. How to look at the signal is different. So it means that somehow we can say that it implies that this quantity is actually, because they're positive, is between 0 and 1. And the same thing for this one. This is also between 0 and 1. And then we can assume that these are probability distributions because they respect the PDF assumptions, so we can assume that they are probability distributions. So if we want to get the mean for the time in the time frequency domain, we can assume that the mean is nothing but integral over t times the PDF, which is exactly what I wrote here, this quantity. That's the mean, definition of the mean or the expectation. The same for the mean of the frequencies. We can get this one. And for the variances, it's just the mean taken out from the t squared times the PDF. And for the frequency variance, same. What do I mean by the mean and the variance of the frequencies? So we have the resolution. Resolution means that how much we are certain about the time and how much we are certain about the frequency. We have a mean for this because it's a random. It's a kind of probabilistic, problem. So we have a mean and we have a variance. So the resolution over the time and the resolution over the frequency. Because we're not certain about that and it's uncertain and it's together with the probability, every uncertainty is together with the probability, we need to know what is this mean and the variance for these uncertain quantities, which are also related based on this time frequency plane. We can assume that this is a kind of surface. Considering that delta t is the standard deviation, so it's the square root of this variance, and the same for the delta f, which is the square root of the variance of the frequency. Heisenberg proved that time resolution over the frequency bandwidths is almost holding this inequality 1 over 4 pi. And this minimum is actually is something that holds for just a certain function. So there's only a certain function, a certain kind of kernel that can hold this equality. But in all the other cases, there is an inequality. And it means that either you want to have a very high time resolution, then it means that you need to sacrifice the frequency resolution, or vice versa. You will not be able to have both resolutions in the finest possible state at the same time. So, there are two ways that we can have this joint time frequency information at the same time. One idea is, okay, what if we chop down this stream of the signal which is coming into the short frames using the window like this. So the size of the window here, for example, is constant. We can assume it's constant, A. And we start from the starting point of the signal, and we try to slide the window over the signal. Okay? So it means that we have a window is fixed and is slide or shifted over this time. By that, we can actually get the frequency representation of the signal within this window for different time views, for different time windows. That's the idea behind windowed Fourier transform. So whenever you see this phrase, windowed Fourier transform, it's a joint time frequency analysis which represents this kind of structure, to have a window, and this type of the window can be different. It can be a Hamming window, Gaussian window, whatever. Doesn't matter. We have a fixed length window. You slide over the signal. Or you want to reconstruct the signal using the atoms, the bases, which these bases are not as simple as what you use in the frequency domain, e to the power of j k omega. But they are a combinatorial or a complex atoms which contain both the informations from time and frequency at the same time. So they are called joint time frequency atoms, HMN in the discrete domain. So you're somehow trying to reconstruct the signal based on these atoms and the amount of coefficients you have to assign for each of these atoms. For this time frequency play, by changing M and N, we can move forward for the time or the frequency. And we know that these coefficients are nothing but the inner product or the projection of the signal over the dual of those atoms. If they are orthonormal atoms, then the duals are the same as themselves. Otherwise, it would be different, but not that much different. Like the Fourier transform, the analysis and the synthesis. E to the power of minus jk for the analysis, e to the power of plus jk for jk omega for the synthesis. So these are the coefficients and these are the atoms. And this view of joint time frequency analysis is called, in general, it's called the STFT, or short time Fourier analysis, or Gabor. Gabor or STFT. So, windowed Fourier transform and Gabor transform or STFT transforms are two different views for the same analysis strategy. So these are the two things we can do if we want to analyze the signal. For windowed Fourier transform, we have the window sliding over the signal. And for the STFT, we take these atoms. They are also dual if you want to know that. So this is, let me first explain this. So when we say that what's the STFT transform over the signal, it means that if this is the signal, Ft, it's the signal, you need an atom for the STFT. This atom is Wt minus tau, which is times this to the power of minus j omega t. I've intentionally written down that is like this. And this G is the kernel, it's the atom of the STFT. So W e to the power of j omega t. And when you want to reconstruct, for the STFT is just the conjugate. For real sense signals, you can put the conjugate, you can ignore. But I wrote down like this. Why? Because this also can have another view. It's like to have the window shifted t by t times, and you can move over the t to the tau times, and you can move over the tau from 0 to whatever, over the signal. So STFT is also like a kind of window Fourier transform, but what you choose as the window is fixed. And probably you have seen several times this kind of graph, or this kind of structure, which is called a spectrogram. A spectrogram is nothing but the magnitude square of the STFT representation of the signal. So the time versus frequency, and every single color that you see here is actually the magnitude square of this STFT over time and frequency. So if you want to have a three-dimensional representation, it's not possible. To be able to represent it, they just represent it with the intensity. For the third dimension, they use the intensity. So these red parts, when it gets more red, it means that it has more intensity. And when it's getting blue, for example, it means that the value is almost close to zero. The Gabor transform is the one that respects this equality. So the most localized window in both time and frequency is a Gaussian pulse. A pulse which looks like this, for example, in general sense. A G of t, a Gaussian pulse, which looks like this, a Gaussian exponential form, which in the frequency domain looks like this. So Gabor transform is nothing but the STFT when the kernel is the Gaussian pulse. So when we say Gabor and when we say STFT, they're almost meaning the same as with an implementation. The only difference is the difference in the kernel. If the kernel is the Gaussian, so if the G of t here, you use the Gaussian, like this, the form of this, then it's Gabor. Otherwise, it's STFT. And the Gabor gives you this equality condition, but it doesn't mean that it's, the localization in time and frequency, it doesn't mean that it's band limited. So the waveform, this waveform, the Gaussian pulse, is actually neither band limited in time nor in frequency, but it's the most localized. If you choose any other kernel, it would be worse in one sense or the other. In general sense, it's the more localized. But still we have the uncertainty principle. So, these are the simple things that I can say about the Gabor, STFT, and so on. There are some drawbacks for the Gabor transform. You might have understood that. Well, in Gabor or STFT, we're mapping the signal in the Hilbert space, energy space, or Hilbert space, into and we give another dimension. So the signal is real by itself. We are giving actually another new dimension to the signal, and that means redundancy. But this is the cost of having another concept, which is time together with frequency. So we are getting something to the expense of losing redundancy. Another issue is that you are restricted by the time length. So any frequency content of the signal, which is higher than that, which actually the wavelength corresponding to that is higher than the time window that we use for the STFT and Gabor, will be lost because we have localization which is fixed in time. If you have a frequency, a lower frequency, it needs actually a wavelength higher than that window, that will not be seen by the Gabor or STFT. That's the second issue. And that's actually the third issue also, which is related to the second one. The windows are fixed. You can do nothing. So when you choose a kind of kernel, it means that you're fixing that area of time and frequency. Delta T and delta F is fixed. And you can do nothing. We have some different types of joint time frequency analysis transforms, which try to actually tackle the first problem somehow. But they will not be able to tackle this general fixed window problem. So we have a Wigner wheel, pseudo Wigner wheel, and many other things. So if you look at, for example, the Wigner wheel, you see that the kernel is, we have, for example, a ZAC transform, which doesn't take actually the Gaussian window or something like that. It takes the signal itself, so it likes a rectangular window and tries to move that. And Wigner wheel also takes doesn't take any other new signal like the GFT, Gaussian, but it takes the signal and it overlaps the signal with itself from one side and from the other side. So it tries to somehow, it removes the signal over itself. See the signal conjugate and different shifting right and left. And then tries to extract out the frequency and time components of time. So we don't want to go through that. That was the time and frequency, joint time and frequency transforms. So we have Filterbanks, we have joint time frequency, and finally we just come up with the wavelets. You'll see that it's quite the same, and it solves almost most of those previous issues that we have as a drawback of Gabor or STFT. So why do we need to have the constant area window? We can just dynamically change it, and that's the idea. We dynamically change. For the lower frequencies, we need to have a long time window. The wavelets should be as long as possible to get the lowest component of the signal. So we make a multi-resolution analysis of the time frequency plane, the time frequency domain. This is multi-resolution. So the resolution for the finer frequency, the coarser frequencies or the lower frequencies, we have resolution in time but not in frequency. We have resolution in frequency but not in time. Then we go further. You have less, so you sacrifice some frequency resolution, but you'll get some time resolution, and so on and so forth. But the importance about the wavelet is that it's more efficient. Why? Because it tries to be implemented in multi-resolution analysis. It tries to be implemented in an orthogonal structure in such a way that every information that you get from any of this, so any of these transforms, any of these analysis parts, you take this information and it's orthogonal to any other information we get. So you don't need actually to get that information again from the consecutive stages which is coming afterwards. So you take this window for the time, you extract this information, and that's all. You never come back to this again. That information is already extracted. Then you go through you chop the window into two. You get this information for the frequency part. It's not frequency, it's just scale. You remove that and you save it, and that's all. You never come back to this again. And so on and so forth. We go further for all the parts. So, in the same way, we have again the same area, but this area is dynamically changing. So we have the resolution over time and frequency. Sometimes you compress it or stretch it, based on whether you need the time resolution or the frequency resolution. Wavelets, here for example, the continuous wavelet transform, they actually use a kernel the same way. Taking from the idea of Gabor, what they do is, this kernel represents two functions, scaling and transforming or shifting. Scaling is done using the A factor here, and transforming the signal is actually applied using this B or shift parameter. So we have we call it the mother wavelet, or the kernel for the wavelet transform, containing two parameters, A and B. There are different types of, so you can see here how the scaling of the frequency and time resolution depends on A. Now, we have different types of the wavelets based on what is the kernel function that we choose. The original, the very beginning, the very first wavelet that was invented was in 1910, almost 100 years ago, by Haar. So the name of this guy was Haar. And what he tried to actually to represent was this kind of kernel. So this was the kernel he chose. And this kernel is called the mother wavelet. It's called the mother wavelet. So by shifting or scaling this mother wavelet, we can try to get any other resolutions, any of those resolutions in the time frequency domain. So this the structure for the mother wavelet in the frequency domain looks like this. So Haar is not a very good wavelet because we see in the frequency domain. So the frequency components go to the infinity from both sides. And the decaying of the curve depends on so it's 1 over omega, it's actually decaying. It's very smooth decaying. And we need something to be fast enough in both time and frequency. It's fast enough in time, not in frequency. If you scale it, so if you choose A to be more than 1, so you are squeezing this curve, and what you get in the frequency would be like this. And if you stretch the signal in time, then you will have more compressed in frequency, look like this. And then by combination, so you have the coefficients C0 for this one, then another coefficient this one, and combination, all of them will give you the signal, the F signal finally. There are some conditions that should be held. So the representation of the continuous wavelet transform will be like this. This kernel of the wavelet transform over the signal, and this gives you the transform, and it means that the signal projected over these kernels will give you the coefficients. That's the same for all the transforms by far. But there are some conditions. Well, these values are all in the real domain. The kernel is symmetric. Positive side and negative side you see here. If this is 0, the negative area and the positive area cancel each other. And it turns out that in order to reconstruct the signal, you have a quantity called C of psi, for the mother wavelet, is a coefficient, which has this kind of equation, this kind of related equation. This should be limited. And just by looking at this, it turns out that the mother wavelets should be band pass filters and not low pass filters. Why? Because for the low pass filters, means omega, for example, 0, the filter should give you some value. If you put 0 here and you have a value here in the frequency domain, then it becomes infinity. So it doesn't work. But if it's band pass, if for the lower frequency 0, for example, frequency, you might get 0. And 0 over 0 is ambiguous. If you try to remove the ambiguity, you will get some number, and it will not be infinity. And the same thing for the higher frequencies, omega infinity and infinity, for example. If you have ambiguous part, you can remove the ambiguity, you'll get some number. But in other case, so you will get the infinity, and this will not hold. That's why this equation, this condition, represents that this side, the mother wavelet, should be band pass filter. And how they design this band pass filter, you can just refer to, you're using the MATLAB code, or you can just refer to one of these notes that I will mention. And I'll put in the website, and you see that you can have the same structure for the filters, just the same as what we had in the Filterbanks, orthogonal wavelets or any other types. So in the same way, we see that the structure that we had for the filter bank is also holding here for there's also holding here for the wavelets. So we have the fine resolution and the coarse resolution for the wavelets. When we take a long window, we are just taking the lower frequency part of the window, the part of the signal, and it's just like the coarse resolution. When you go to the details, then you are having, it's just like to have this part of the filter bank. So in the filter bank, in the wavelet multi-resolution analysis, we are just somehow implementing the same idea, but with different notion. Here we have the notion of the frequency, and in wavelet we have the notion of